Uh, Good evening, everyone, all four of you. And it's still 1 minute before, so nobody is late. And I will wait a little bit till after 6:30 to begin. And in the meantime, I will get everything set up. I think I've already done it, but oh, excellent! It's actually all in the same. Okay, that. There we go. Perfect. Well, I will start slowly and build up to an excellent crescendo. Actually, I'm going to get a glass of water because my throat's kind of dry. anyone's just joined, I haven't said anything yet, so don't disconnect and reconnect thinking there's something wrong with the audio. There isn't. I'm not talking. Let me finish this Zoom chat message and we will get started. Let me build a model later. See, last part of the question. Units. There we go. Okay, good. Good evening. Welcome to lesson 8 of CE 3372 Water Systems Design. And I hope you've all had a great day and a great week. And today's lesson is pipe network analysis. A bit of the review of the theory of network simulation, as well as some requisite arithmetic. And we are leading up to actually simulating network behavior for flows and pressures. And we're going to look at doing it ourselves in terms of writing our own programs. And then we're going to use that as a way to inform ourselves how to use the professional tool EPANet. In reality, we probably won't get entirely through today's lesson. I mean, I'll get to the end of the slides, but it will be unclear, and so we will pick up next meeting and use part of next meeting to finish up the theoretical background and get started with the EPANet model. So don't be afraid if at some point I go seemingly fast. It's not by design, but it is a consequence of what used to be 3 lessons being squashed down into 1 to be sure there's sufficient room for some other topics. All right, with that said, I'm at the blackboard for section 1, which is our section. I want to bring your attention to, I believe, let's see, let me see if there's any outstanding quizzes. There's quiz 3 and 4 have been posted, and the other 2 have not been activated yet. So if you're up to date on 3 and 4, you're good on the quizzes. We'll probably activate them tomorrow so that they activate the same time for both classes. And let's see, homepage. I know you're working on the exercises because you're sending lots of emails, and that's fine. And that's it. So I think you're working on exercise set 3, and then exercise set 4 would be the next one. And it's pretty straightforward. It's mostly a review of the head loss models. And with that, let me return to the actual lesson. So taking the link or the folder takes us to the link. And even though it's obviously already up here, I actually want to generate a new tab. And it did that. Okay, good. So here is the content server page for this particular lesson. And you'll notice the lesson title hasn't been established yet. The description's blank, but this is a network simulation. And there's quite a bit of available reading, although I just noticed that this one, hydraulic notes, the link is failed, but that one's good. That one's good, fortunately. That one's good. So is that one. Good. And this one we're actually going to visit in earnest. That was a broken link. That one's open. That one works. Yay! Almost done. Sweet. Also for this lesson, in the data links section, there are quite a few examples, both in Excel spreadsheet and the R scripting language. So this is a scripting language to do what I'm going to talk about today. And let's see, problem 2, 3 should also be in R, and I think problem 4 adds pumps. Yeah. Okay, so we're probably not going to get through all those today. So let's begin with the notes. Let me first suggest that this one, Hydraulics of Pipelines and Pipe Networks by Werbs and James, is probably the most useful read if you feel like you've never done this or you've completely forgotten these concepts from fluid mechanics. It's not very long, and it's in classic textbook style, which most of us are accustomed to reading, and goes through the kind of old-fashioned setup and where it becomes less useful for current use is when we get to the latter part of the reading, and it discusses how networks are simulated. As I'm scrolling down, doing this on purpose, not just to make you nauseous, although that is always a daily aim. I'm trying to check and see if they still use Hardy Cross by the loop equations, which I think they do. We'll actually do this problem today. There we go. Network systems has an example, sets up the node arc incidence matrix. And yes, they do the Hardy Cross method, which is quite obsolete. The reason the method is obsolete, well, I'll get to that in the presentation part. So that one is worth reading. There's a couple of papers here. One is determining friction factors for commercial pipes. You notice Darcy Weisbach and Hazen Williams are friends, and that particular set of data should look awful familiar because that is the laboratory results, which are combined with the results of quite a few other people to generate those the Moody chart. That is the original source of the Moody chart. And this paper goes on to provide modifications to equations and how to compute friction factor for different materials. So that's an interesting read if you ever encounter a case where what you're looking for is not well documented. I just noticed I have this repeated twice. That's interesting. And the next comment is this paper by Hayman and Bramiller. This is from 1971. This paper is the algorithm that ultimately has become incorporated in the EPA-NET model. The commercial versions of the EPA-NET model, KY Pipes, which is another commercial network simulation model, and parts of SWIM actually use elements of this. And then I forget what the European model is for network simulation, but it uses the EPA-NET computation engine. So this seemingly obscure paper from 1971 by a couple of engineers in mechanical engineering published in an electrical engineering document is the basis of all modern hydraulic models used today. And actually without much change from this original paper. So in the olden days, universities would have made you read this paper and figure it out on your own. We're going to do a variation of that. I'll have it kind of figured out already. And it discusses how to create the algorithm. One of the modifications is this part on constructing the tree, which is called a traversing a directed graph, can be illuminated by a subtle repartitioning of the matrices described in this paper. And I'm going to present them as if that's already known. So let's go on with the lessons. So the PDF contains what we're going to look at today. You'll notice the file structure has changed from PowerPoint because my PowerPoint software doesn't work in the new operating system, and I am too stubborn to pay Microsoft to get it to work. I paid them once for a perpetual license, and perpetual, that word means to me forever. It doesn't mean, oh, in 5 or 6 years we want more money from you if you want it to keep working. So I think that's pretty bad business on their part. Ultimately they'll win, but for the time being I feel somewhat satisfied by finding a workaround. So this is done with some freeware. As such, it's not quite the same, but I did the best I could to preserve the look and feel for the remainder of the semester. So let's begin with the lesson. So the topic is network hydraulics, and we're going to review hydraulic principles. And I'm pretty sure you had most of this in some form in your fluid mechanics course. But here we're going to try to tie it all together, and then we're going to go straight into how you would do computation in building the resulting system of equations for a network. And then we won't get to adding pumps today. We may get to that slide, but we won't get into any details of it. So the principles of network hydraulics are first, there is a set of conservation principles that's applied at a junction, and they're called nodes. So they're nodes in your exercise set as an example. And that's simply says that the sum of the inflows minus the sum of the outflows is 0 at a node. And there's a couple of conventions that are used. Positive demand at a node is treated as an outflow in terms of that equation. And negative demand, or if we put water into a node external to the network, so the water comes from somewhere else and we're pushing it into the network like an injection, that's negative demand. That's considered an inflow. The positive demand, that water leaves the network. So once it leaves the network, it doesn't come back in. So it goes through kidneys and colons and on into a wastewater collection system. It's no longer part of the drinking water system. For each node in a network, and by that I mean a network model, well, it's theoretically possible to model down to the connection level, and there are probably models in use right now that actually go to that level of discretization. It's not a smart thing to do unless that's your full-time job, for two reasons. One, the models get quite big. I mean, they still fit in the computer because bits are small. But they have quite a lot of parts, which makes it hard to maintain the model, hard to diagnose mistakes. And secondly, if it gets too big, the computation time isn't much faster than waiting for things to happen in the real world, which kind of defeats the whole point of a hydraulic model and automated control. So we have one balance equation for each node. We also stipulate that at a node, the head is a single value. So the head isn't different on the left side of the node than on the right side of the node. And even though in real systems these junctions might they occupy finite space, they have dimension, that is generally ignored in a pressurized pipeline model. So node is a single point where miraculously pipes of vastly different diameters at different elevations can all come together and participate in their conservation of mass behavior. The head at the node is usually expressed as a pressure, or it's usefully expressed as a pressure, and we can visualize that as the height that a column of water in a piezometer would rise to in a junction. So in this picture here on the right side of the slide, here's our junction, the pipe coming in, a pipe leaving, and demand leaving, and there's this pipe that's stuck to the junction that goes up into the sky. And the pressure head is how high water would rise into that pipe. We combine that pressure head with the known elevation of the junction, and those two added together become the total head at the junction. The total head is really what we calculate, and then from the known elevations we recover the pressure head at each point, and then that pressure head we can test it against our design guidelines, 35 psi for example, to find if our system is satisfying those requirements. The other principle that we have is conservation of energy along a conduit. And unfortunately, I can't actually draw on this. This red line isn't correct. The red line is supposed to go from that location where the cursor is circling around right now to that location. It's supposed to go this way. So I'm moving the cursor back and forth, so you got to pretend that there's a red line there. The red line that's shown here moved when the slides were translated from their old PowerPoint version. So conservation of energy along a conduit is simply the modified Bernoulli's equation, including all known losses, and it simply says that the total head at this node, in this case the left node, minus the head loss going to the right node is equal to the total head at the right node. So we have total head here equals total head here minus the head loss. And so that gets us to these two heights that represent the pressure head at each node. And for each link in a model, each pipe, each conduit, there'll be an energy equation for each link. Now, I've presented this graphic here as if the pressures are unknown at each of these links, each of these nodes. This is not a good time. Here, stay there. As if each of these are unknowns, it's quite possible that the total head is known at a particular node. That would be called a fixed grade node, and in fact every functioning model is going to have a fixed grade node somewhere. But for the purposes of a systematic way of assembling equations, we will initially pretend that we don't know the heads at any of the nodes, and at the end when we do equation assembly is when we incorporate the known fixed grade nodes into the equations. And they appear on the right hand side, and we'll get to that shortly. So to motivate these ideas, let's first look at the simplest of network structures that we can visualize. There's two simple ones. First is this one, a branch system. The next one is a looped system. And let's examine this equation assembly process. So in this picture, we have three reservoirs, and they're all connected at a common junction labeled D. And there's these pipes that connect each of the reservoir to the common junction. And there's these little arrows that represent flow velocities in each of the pipes. And the choice of flow direction initially It simply establishes the algebraic sign of those velocities or the discharges, which are velocities multiplied by area, at the solution. The unknowns in this are the three flows in the pipes and the unknown head at node D. So that's a total of 4 unknowns. And we would need 4 equations to solve simultaneously to find unique solutions to those 4 unknowns. And the 4 equations are the one node equation, the one continuity equation at node D, and the 3 energy equations for each of the pipes. And if we were to pull those out of the diagram, we would have the energy equation for pipe AD is this first one here on the right side of the figure. And it simply says the total head at reservoir A is equal to the total head at reservoir D plus the head loss from A to D. And the unknowns are this green box, which represents the elevation of node D plus its pressure head, and the rose box, which represents the velocity in pipe AD, in this case squared, using the classic way of writing Bernoulli's equation. We repeat that for the BD connection, the second equation, and then the D to C connection. The D to C connection looks like it's different, but you could have the same structure if you moved Z sub C to the left, put a minus sign in front of it, and move this green box to the right and put a minus sign in front of it. You would then have the same structure to the equation as the other two. Here it's written as a classic Bernoulli equation. So total head at D equals total head at C plus the head loss from D to C. And the fourth equation is a continuity at the node, which recovers the 3 velocities, or the 3 flow rates, if you will, at the node. So we have these 4 equations and 4 unknowns. It turns out that they're nonlinear because of the squared term in the head loss part. So we would have to solve it by an appropriate technique for solving nonlinear equations. And one of them, it's in common use, is called the Newton-Raphson method. And you had that in engineering 1331, whatever the computer class is, the MATLAB class. You were supposed to have been introduced to nonlinear equation solving there. A second technique is quasi linearization. It's almost the same technique operationally. It differs by a constant of 2, but other than that, it's the same method. And these equations are quadratic in the unknowns, and so normally we can obtain a solution in a few iterations. The second structure is a loop structure. So here we have these 2 nodes that are shown by blue dots, and they're connected to each other through 2 different pipes. And going from this node in the lower left-hand corner, we can traverse pipe number 2 here. We get to this node, and then we can reverse traverse pipe number 1 and get back to the original node. So that's what's meant by a flow loop. The total head loss around that loop is algebraically 0, because in this part of the traverse we're going in the same direction as flow, and in the reverse part of the traverse in the other pipe we're going opposite the direction of flow, so we regain the lost head. And in a loop system, the node equations have the same properties, inflow equals outflow, and the link equations still have the same head loss equations, but historically we observed that head loss in any loop is 0. So if we had a way to identify all the unique loops in a network, we obtain enough equations to solve the problem. But in doing that and choosing the loop approach, we essentially lose information about the pressures, and we have to recover them later. So here's a branch system with numbers. It's the same drawing as before. And we're actually going to go through this in a different document. So I'm going to go through these quickly. I'm not going to comment on them. We'll go to the other document. But when we get after the algebraic analysis, here is a spreadsheet that finds solutions to that branch system. I want to go to one of the readings, and in the reading from CFM in R, Computational Fluid Mechanics in R. If you hear strange noises, there is a cat that is attempting to operate the keyboard and the mouse. And he means well, but he's not a very good hydraulic engineer, unless spilling over hydraulics. He's excellent at that. So let's do a quick review of the Newton-Raphson method from a computational approach. If you recall Newton's method for scalar valued functions of a single variable, we do a Taylor series expansion of the function, truncate every term after the first derivative, rearrange it, and what we can obtain from that is a recipe for updating an initial guess x sub k. And so the update is equal to the old guess minus the value of the function at the old guess divided by the first derivative of the function evaluated at the old guess. And that gives us a new guess. And what that's doing is it's trying to drive the value of the function to 0. So we stop when we find a value of x that makes the function equal to 0. Now we want to do it in multiple dimensions. So here's an example of a function that's constructed of two equations, equation 1 and 2, and equation 1 is x squared plus y squared minus 4, equation 2 is e to the x plus y minus 1. And so we're looking for values of x and y that will make that function evaluate as the vector 0, 0. So what we need is an analog for the derivative, when we go to vector valued functions, and we need an analog for division of a vector by a matrix. So the analog to the first derivative is a matrix called the Jacobian, and it's comprised of first derivatives of the function f with respect to the individual arguments. So the Jacobian for this equation up here, for equation 65, would be the matrix that's comprised of the partial of f1 with respect to x1 in this corner of the matrix, the partial of f1 with respect to x2 in that position of the matrix, the partial of f2 with respect to x1 in this position, the partial of f2 with respect to x2 in the lower right position. And this scales in both directions as the number of functions and the number of independent variables increase. So the way you can think of it is the first row of the Jacobian is the first equation of the function differentiated with respect to each of the different variable values. The second row of the Jacobian is the second equation of the function differentiated with respect to each of the independent variables. The third row is the third function, so it has the number of rows that's equal to the number of function equations, and the number of columns is equal to the number of independent variables. So if you recall that in matrix arithmetic, there is no such thing as division, but there is a multiplicative inverse of a matrix. And so if that inverse exists, the equivalent of division is to multiply by the inverse of the Jacobian. And so the multivariable Newton's method is written as the new value of x, which now is not one thing but two things, is equal to the old value minus the inverse of the Jacobian times the current value of the function of x. inverting a matrix is computationally quite expensive, so the linear algebra identity that we employ is to multiply both sides of that update equation by the Jacobian at the current guess, and what that leads to is a linear system of equations. So the negative of the Jacobian times the change in the values of x is equal to f of x. So we know the Jacobian, we know the f of x, we don't know x of k plus 1 minus x of k, but we do know x of k, so we can solve this linear system at this instant for everything here in the parentheses. And then once we have that, we subtract x of k from it, and that gives us the new update. So here it is in terms of steps. We would start with some initial guess, compute the function, compute the Jacobian. We would then test if there's any point in continuing. So is f of x close enough to 0? If yes, you exit. If that's not the case, you continue. Then we solve the linear system minus Jacobian of x minus Jacobian of x. There's a sign error here. There should be a minus sign right there. Times the change in x values equals f of x. And then we make another test. Was the change real small? If there is, there's no point in continuing. We can quit. If that's not true, we continue, and we compute the value of the update. So x of k plus 1 is equal to the old value, x of k, minus the computed change in x, which recovers x of k plus 1. Then we move the update back into the guess vector and go back to step 1 and repeat it. So if we look at that example, here's the function. Here's the Jacobian written as an analytical matrix. And here is the required script to find the solution to this equation 73, where we're trying to find the value of x, which is x and y, that makes f of x equal to the vector 0. So we would have to define the function, which is done there. Define the Jacobian, which in this case is explicitly, the matrix is explicitly built. And then we set up some parameters to handle the iteration count. And we have our initial guess, and then we have the result of our update. And the first pass through, the initial guess and the updated value are the same thing. And then we run through the Newton-Raphson algorithm. So we iterate, we calculate the current value of the function, we test if the function is small enough, then we compute the change in x by solving the linear system of Jacobian times dx is equal to function now. Again, test for time to quit, and then perform the update, and we return back up to the top of the iteration. And then when it's done, we print the results. So that's cool, but it is somewhat inconvenient to have to program in the Jacobian as an analytical matrix, which in the case of a pipeline network, if we have thousands of types and thousands of nodes, programming of that could be a monumental hassle. Fortunately, the Jacobian for a pipeline network is very much determined by the node arc incidence matrix, the count of the pipes coming and leaving nodes. And so all we need is a little bit of computer logic to compute that matrix for us. What we do in the case of pipelines is not a finite difference approximation, although one could do that. I don't think that would be advantageous. And Here's the Newton-Raphson for that particular problem. It turns out that the value of x and y of 1 and minus 1.77 will make that equation pair close to 0. So now we move to pipelines and networks. So all I did was want to review the Newton's method. So in terms of network topology, we have this principal, continuity at a node, and we've seen this drawing before. We've seen this drawing before, and we have energy loss along a link, and we have the definition of velocity head, added head of pumps, and extracted head of turbines. Okay, so all that is review from previous lessons in this semester. Then we have a couple of different head loss models. In this presentation, we'll be using Darcy-Weisbach, but you could easily use Chesney Manning and Hazen-Williams with appropriate changes in each of the head loss models. So that's the Darcy-Weisbach equation. We need some way of obtaining the friction factor. We know the friction factor is a function of Reynolds number and roughness ratio. We may not know the structure of that function. There are quite a few equations, and the one we're going to use is the Jane equation, which provides the friction factor as a function of roughness height, Reynolds number, and some constants. So this is like all the other ones. This is simply a logarithmic fit to those observations that I showed you in the paper by Singh and all. So we have this function. So that's for what it is taken from the literature. It's a table lookup, but we're going to do it in the computer. And then we want to solve our pipeline network. So we've already stated continuity is written at nodes, and what this produces is a set of equations called the node equations. Clever nomenclature there. And then we have energy loss written along the links. That produces the pipe equations. The equations are assembled in a particular structure that we can take advantage of computationally in order to find the simultaneous solution. And the solution technique that's going to be used is Newton-Raphson. So let's use this particular example as a way to illustrate the algorithmic features that one would have to do if you were doing this by hand or in a spreadsheet. And then we'll run a few examples of this in the R script because it's already built. And that will set us up for next time when we talk about incorporating pumps and moving on to the EPANet computer model. So here's a network depicted here in the picture. There's a single reservoir labeled H sub 0 that has a pool elevation of 100 feet. That turns out that happens to be a fixed grade node. And I have intentionally labeled the head there as H sub 0. So you can think of that as node 0 for the purposes of final equation assembly. Node 0 never really appears in the equations, but we'll get to that when we get to it. And it's connected to node 1 through pipe number 1. There's only one pipe, and we have arbitrarily chosen the flow direction from the reservoir to the node, and we've drawn a little red arrow to indicate that direction. The consequence of doing that is that red arrow now establishes the algebraic sign of the solution of whether flow is from the reservoir to the node or from the node to the reservoir. If we recover a positive value for the flow in that pipe, then the red arrow and the actual flow at the solution are in the same direction. If we recover a negative value, then the flow is opposite to the red arrow. At node 1, there's two pipes leaving, pipe 2 and pipe 4. We get to node 2, and there's pipe 2, pipe 6 coming in, pipe 3 leaving, and the demand of 4 cubic feet per second leaving. We move to node 3, and we have pipe 4 coming in, pipe 6 leaving, pipe 5 leaving, and 3 cubic feet per second of demand leaving. We get to node 4, we have pipe 3 entering, pipe 5 entering, and 1 cubic feet per second leaving. So it's trivial in this particular example to figure out what the flow is in pipe 1. Because as drawn, the flow is likely from the reservoir to the network, and all the demand had to pass through pipe 1 at some point in its life. So the flow in pipe 1 should be 4 plus 3 plus 1, 8 cubic feet per second will go through pipe 1. So pipe 1 is really not an unknown, but we're going to proceed as if it is. And that gives us an independent check at the solution if it found a solution that makes sense. Additionally, we have the individual pipes named, pipe 1 through 6. Here's their lengths in feet. Here's their diameters in feet. And we have the roughness height for all pipes is 1 times 10 to the minus 5th feet. They can have different roughness heights, and we would carry a roughness height attribute along with each pipe. And the viscosity of the water is taken as 1.1 times 10 to the minus 5th feet squared per second. And that information is used when we're calculating Reynolds number to find the friction factor. So one of the nice things about the Hazy-Williams model, we don't have to keep track of viscosity or roughness coefficients because they are directly incorporated into the Hazy-Williams loss coefficient. So let's proceed to assemble some equations and try to do Newton-Raphson. So our first thing is our unknown vector x. And I have chosen to organize x as q1 through q6, h1 through h4, where the h's represent the total heads at their respective nodes. So h1 is the total head at node 1, h2 is the total head at node 2, h3 is the total head at node 3, h4 is the total head at node 4. And then the q's are the flows in the pipes. q1 is in pipe 1, q2 is pipe 2, and so on. If we were to analyze continuity for each node, we'll have 4 equations because we have 4 nodes with unknown heads. Node 0, we know what its head is, so it doesn't have to appear in the system directly. And for instance, node number 2, the equation is Q2 coming in, Q3 leaving, Q6 coming in, and 4 CFS leaving. So we have Q2 coming in, Q3 leaving, Q6 coming in, equals 4 cubic feet per second on the right-hand side. We move the demand to the right-hand side. We would repeat that for nodes 1, 3, and 4 to get the node equations. Next, if we define head loss in any pipe as the change in total head for the pipe using the Darcy-Weisbach equation, we have the change in head in the pipe is equal to the friction factor times 8 times the length of the pipe divided by pi squared g divided by the diameter of the pipe to the 5th power multiplied by the absolute value of the flow rate in the pipe times the flow rate in the pipe. Nico. And this absolute value, using that in establishing what is essentially a q squared term, by breaking one of the q's into an absolute value, we're going to keep the absolute value with the rest of the Darcy-Weisbach equation and recompute that at each flow guess, but the remaining q sub I carries an algebraic sign, either positive or negative, which will identify flow direction. So, actually, it may let me do this today. So everything in purple there, we're going to rename that capital L sub I, and we'll do that for each of the pipes. And so, for instance, pipe number 2, the pipe equation is pipe 2 is the total head at node 1 minus the head loss in pipe 2 equals the total head at node 2. So here we have the total head in node 1 minus the head loss in pipe 2 minus the total head at node 2 equals 0. So it's the same equation rearranged. And it's rearranged to have a particular structure because we're setting it up that the head values are in the correct columns and the loss values are in the correct columns with respect to the rows that are determined by our unknown x vector. If we write all the equations for the pipes and the nodes and split off the right-hand side for the time being, here's what the matrix for that problem looks like. We have 1, 2, 3, 4 node equations, 1, 2, 3, 4, 5, 6 head loss equations. The plus ones, the minus ones, and the zeros in the node equations indicate that that particular node is connected to the pipe where there's a 1 and the flow direction is into the node, and it's connected to a pipe where there's a minus 1 and the flow direction is out of the node, and when there's a 0 it's not connected to that variable. So you notice this block of zeros here for the heads. That is because the total heads at each node are irrelevant in terms of the continuity equation. We have to keep the zeros there for algebra reasons. Down here in the pipeline portion, we simply have the starting node, ending node, and then the pipe identifying the connection between the two. It turns out that this block of variables in the lower right corner below the horizontal line, this partition, and this block in the upper left corner are the transpose of each other, and one of them is multiplied by -1. So that's a handy bit of information because it means to actually solve one of these, the only thing we need to supply is just that partition. So the node arc instance matrix is all that's required to build a network simulator. And that is a consequence of the 1971 paper by Hayman and Bray. And prior to that, there were elaborate loop counting schemes that were required to solve a smaller set of equations, much more compact than this. But their scheme allows the thing to be built quite easily. So now we have to consider the right-hand side. So the first 4 entries in the right-hand side vector correspond to the 4 nodes, and what goes in the right-hand side then is the demand for that node. If the demand's positive, water's leaving the node. If the demand is negative, it's entering the node. So we had no demand at node 1. We had 4 units at node 2, 3 units at node 3, and 1 unit at node 4. And then moving into the pipeline model, this particular case, we set it up so that the first row of the pipeline partition happened to correspond with our fixed grade node. And if we'd had a node 0, which would have come between these 2 columns, we would have had a 1, we would have had a H0, total head at node 0, minus L1 equals total head at node 1. Well, so we have to take that total head at node 0 that would have been there if we cared about it and move it over here to the right-hand side and change its sign so that 100 units of head at the fixed grade node appears here as a minus 100. The remaining pipes energy is completely conserved, and because we don't know the heads, we enter zeros here. And so this is our right-hand side. And so our system expressed as a linear system is a of x times x equals b. And that's what we have to solve. So that's not linear because of the dependence of the coefficient matrix on the values of x. And that dependence occurs in each of these capital L values that are computed using the Darcy-Weisbach formula. So if we assembled the whole thing like we would do back in our calculus class, it would look like this system here. And all we need to do now is find a way to solve it. So we would guess numerical values for the Q's and the H's. Once we have numerical values for the Q's, we can compute the values of L, and that's, at that point, that's now a linear system. We solve that system, and we'll get a new value of Q's and H's from the solution of that linear system. We use the new Q's, recompute the L's, and solve it again for yet a new guess. We keep doing that until this vector is not changing, and until the error between the solution and the right-hand side goes to 0. So everything I just said is here in writing. So moving along, that's what we want to solve. It's nonlinear, and so we want to take advantage of some structure, and we're going to apply the Newton-Raphson method as an algorithm to solve this system of equations. So a script has to accomplish several tasks. It has to read the node-arc incidence matrix. So it has to have a way of getting that partition, and the rest we can build once we know that partition. It has to take an initial guess. We, the analysts, have to provide that. And that initial guess has the added bonus feature, it can't be 0. If we put a bunch of zeros in here, the algorithm cannot proceed, and yet it will still be wrong. So we can guess 1s or 3s or 7s or any number that we like. So for this particular problem that we have the drawing of, right there, here is an input file that will correspond to a particular algorithm structure. So let me point out the input file. Number of nodes, number of pipes, diameter of the pipes, the length of those pipes, the roughness height for each of those pipes, the viscosity of water, so this one's going to be using the Darcy-Weisbach equation and calculate Reynolds numbers, an initial guess for the flows. We don't necessarily have to make an initial guess for the heads, but we have to make an initial guess for the flows, and it can't be 0.
Okay, you're going into the cage.
The node-arc incidence matrix is right there. So there's the node 1, node 2, node 3, and node 4 continuity equations. And then the last part is the last row is the right-hand side. That's literally all that's necessary to find solutions to that particular network. What our program will have to do is we're going to have an ability to compute Reynolds number as a function of flow. That's fairly straightforward. We can do it with this formula here. Once we have Reynolds number as a function of flow, we can compute friction factor as a function of roughness, height, diameter, and Reynolds number using the Jane equation. That's shown right here. And finally, once we have friction factor, we can compute the capital L coefficients that go into the coefficient matrix and its Jacobian using formula 95 shown here. And these support functions can be encoded into a script like that. There's really not much to it. Here's a Jane friction factor, and this happens to be in R, but if you're familiar with Python or pretty much any other scripting language, MATLAB has very similar syntax. Here we define a velocity function, and we're calculating velocity as a function of diameter and discharge in order to compute Reynolds number. So we have a Reynolds number function. And lastly, I call this the geometric factor function. And the geometric factor is, get this right, it won't let me highlight it. It's the 8li over pi squared g d to the fifth right here. It's just this term that's in the middle of the group of terms in equation 95. So friction factor has its own function. The geometric factor has its own function, and we'll multiply it by the absolute value of Q for that particular pipe as needed. Then we need to build the matrix, the A matrix. That can be built from just the node arc incidence information, because that part doesn't change, and whatever the current values of L are. We also need to build a Jacobian of A to use in the Newton-Raphson update. That is not as difficult as it sounds, because it turns out that in network models, the Jacobian of A is almost identical to A. It differs by a factor of 2 in only one partition, one quadrant, if you will, of the matrix. And that's predictable, so we can put that logic into any computer program that's going to do these calculations for us. So this repeats the whole Newton-Raphson method that was showed you above, only uses the right letters of the alphabet for this problem. Ultimately, here's what we're solving is Jacobian times delta x equals this right-hand side. And here are the rules for the Jacobian. The partition in the matrix corresponding to the node formulas in the Jacobian are identical as those in the original coefficient matrix. So we will have zeros, plus ones, or minus ones in the same pattern as in the coefficient matrix. The partition in the matrix that corresponds to the pipe head loss terms, the lower left partition, will consist of values that are twice the values of the coefficient in the original coefficient matrix. The partition that corresponds to the head terms, the lower right partition, is identical to the original matrix, and the partition that corresponds to the head coefficients in the node equations is identical to the original matrix. That's a pretty huge simplification. We simply copy the three partitions that don't change into the Jacobian, and the one partition that does change, we have to multiply it by 2 and put it in the right location. Then there's the stopping criteria. We have to stop this thing, because the way it's developed, it'll go on indefinitely. And so we stop under a couple of conditions. The first one is that the f of x term, which is a times x minus b, if that gets close enough to 0, we stop. If the update's not changing, we're not getting anywhere. The algorithm is either at an answer or it's stuck. So we stop. And if we've done a bunch of iterations, say we've passed 100 times through this thing, and we're not getting anywhere, there's no point in continuing. We stop. So here's a code fragment that implements the Hayman and Bray solution. And first it reads the input data. So all this stuff that's highlighted, its purpose is to read that input file and put the numerical values in the right places and in the right objects. And then there's a portion here that's attempting to echo the input back to us. And this is used in diagnosing mistakes if you're making your own script. Then there's the part that builds the A matrix, except for the loss terms. Then we have a portion that is just initially creating space for keeping track of things. And now we compute the geometry factors. And we wrap all of those computations into right here. That's the Newton-Raphson loop. So it's going to do that over and over again until it finds a solution. First thing we do is we find the current velocity based on the current guess, current Reynolds number based on the current guess, current friction factors from the Jane equation, current loss factor from friction times geometry factor times the absolute value of the flow guess. Then we build the function matrix. So this is where we actually build the A matrix, is right there. That's all that has to be built in the A matrix, and we're only working on the partition that matters. The node arc instance matrix is already built. It's in the augmented matrix. The transpose of it in the correct location is already there, and the bunch of zeros that corresponds to the heads in the node equations is already there. All we have to do is deal with that main diagonal and put the loss factor term in. Then we build the current Jacobian, and so the easiest way is we simply copy the current augmented matrix and then repair the part that corresponds to the portion where we have to multiply by 2. So you notice the counting of this row and that row are the same. Now we build the augmented matrix times the right-hand side at the current guess minus the true right-hand side. So this is the function we're trying to drive to 0. And we solve the Jacobian matrix times that augmented matrix times the current guess minus the right-hand side for the update, which is dq. And then we perform the update. We take the current guess, we subtract off dq, and that gives us our new guess. Make our tests for stopping, and if that's not the case, we go ahead and perform a formal update to put the guesses into the right place and redo the loop. And then when we're done, we start to report results. And so here is that exact problem done for you, but I'll run it live in a second. So that takes us to, kind of cool, we got to skip a lot of PowerPoint. It's always a good day when you get to skip PowerPoint slides. So I mentioned Hardy-Cross. I showed you Newton-Raphson technique, but we didn't do the node plus loop equations. And then what we just went through was the hybrid method by Hayman and Bray. And this is the example we're working on. Continuity is everything from the document. And we get to the end, and I'm going to stop here, and we'll go ahead and actually run these scripts. So the scripts I'm about to run are from spreadsheets and scripts, and I'm going to use problem 1. I'm going to use this R script. I already have it downloaded, and the only thing I have to change is that is not the correct pipe network for this problem, but it's easy enough to change. Oh, hopefully I've already done it. There we go. So this is our problem of interest, and let's verify that by looking back at the... Don't do that. It's designed to make you make a mistake. Let's go back and look at the original input file and be sure it's what I think it is. So if we look at it, 4 nodes, 6 pipes, 1, 2, 3, 4, 5, 6 values for diameter, 1, 2, 3, 4, 5, 6 values for length, and it looks like this is set up in feet. 1, 2, 3, 4, 5, 6 roughness heights, a value for viscosity because it has to go somewhere, an initial set of flow guesses, which in this case are all ones, the node 1 equation, so pipe 1 comes into node 1, pipe 2 leaves node 1, pipe 4 leaves node 1, the node 2 equation, pipe 1 comes into node 2, pipe 2 comes into node 2, pipe 3 leaves, and pipe 6 leaves. Excuse me, pipe 6 comes in. Node 3, we have pipe 4 comes in, 5 leaves, 6 leaves, and node 4, pipe 3 comes in, and pipe 5 comes in. And then we have the right-hand side. The first 4 represent the demands at nodes 1, 2, 3, and 4 respectively. This minus 100 represents the head at the fixed grade node, and then the rest of them are zeros because there's no further information. That is our pipe network. And here is the simulator. And I'll run it with RStudio. It has some this in Zoom is designed their stuff to get in the way. Like everything computational, it's made to get in the way. All right, I've gone through this scripting sheet already in pieces in the presentation, so I will just scroll down, and the hardest part is reading the data and then converting the various rows that you read, because they're originally read as strings, into their numeric equivalents. And then creating the matrix is easy once you figure out the indexing scheme. And this part is just setting up the actual solution. And then here are the functions. And if I press on this button called source, what it's going to do, it's going to execute each row of this script in order from the top to the bottom, and attempt to implement Newton's method. So I run it, and of course it works because I checked that earlier today. And so here's what comes out. 4 nodes, 6 pipes. It's incapable of returning the length vector because I didn't write the message call correctly. It can't return the diameters or the roughness. Has a fluid viscosity. Initial guess, it doesn't tell us what that is. And it can't do the node arc incidence matrix. So pretty much what there is there's room for all those reports. And if something goes wrong, we can modify the script slightly to recover those terms as needed. In this case, it works fine. It took 14 iterations, and it comes up with an end result. The flow in pipe 1 is 8 units, which is what we knew it would be. Pipe 2 is almost 4. Pipe 3 is 2/10. Pipe 4 is 4 units. Pipe 5 is 7/10, and pipe 6 is 3/10. And more importantly, it's also returning the total heads at each of the nodes. So the total head at node 1 is 84, 2 is 55, 3 is 56, and 4 is 55. 4 was the rightmost node, so it makes sense that it's the smallest. And what we see here is actually considerable head loss going from the fixed grade node into node 1. There's 16 feet of head loss in that first pipe. And then there's another almost 30 feet of head loss getting to the endmost node. So if the node elevations were input, then we can recover the pressure heads and find out if we have pressure at the right PSI. We also having it return the friction factors. The reason we want to do that is mostly to check our work. Those numbers look about typical from the Moody chart, so it didn't screw that up. And we're also returning pipe velocities. And those velocities, 10 feet a second and bigger, is simply too big. So this program is telling me that these pipes need to have their diameter increased. Okay, so that's just a lot of calculation. What was the point of that? Well, the first is we observed that pipe 1, 2, and 4, the velocities are too big. So let's increase their size a bit. We'll make pipe 1 1.5 feet. It says 2 needs to go up. We'll make 2 1.5 feet. And 4, we'll make it a big pipe. Okay, so I just changed 3 things in a file, rerun the script, and now our velocities are quite a bit more reasonable. Notice there's quite a bit less head loss in the system, and that was way faster than doing it by hand or doing it by Hardy cross. The other thing we can examine is see if I can get negative heads here. Let's suppose the fixed grade node, instead of being at 100 feet, is instead 20 feet of head. So not very much. Well, actually, let's just go to 1 atmosphere. So we'll put 30 feet of head in the fixed grade node. Since we haven't specified node elevations, we can initially play the game that they're at elevation 0, and we'll see how much head is remaining in the system. Rerun the thing again and find out that actually that works pretty good because we increase the pipe diameters. But if this particular node, for instance, let's say it was at physical elevation of 20 feet, there's only 7 feet of pressure head available. So 7 feet of pressure head is almost 1/4 of an atmosphere. So 1/4 of 14 pounds per square inch, about 3 pounds per square inch. There's not enough pressure there to meet a statutory requirement. So that's how we use these tools. So that was a example, and let's finish off the presentation. So we've done it without any pumps in the system. If we want to add a pump replaces a link somewhere. So we simply would replace one of those pipes with a pump, and then we actually have to change the head loss model. And the head loss model for a pump is the added head of a pump is equal to the shutoff head minus some pump coefficient times the flow rate of the pump raised to some exponent. Usually the exponent is we're trying to shoot for an exponent of 2 to get it close to a squared, but not all real pumps have that. And we can approximate this equation from a manufacturer's pump curve. And so if we want to do the analysis with a pump, we're going to simply, in this example, I chose to place the pump in place of the pipe 1 and then repeat the analysis. And so all it changes is the pipe 1 equation is replaced with a pump, and The actual pump curve function is built in a fashion like the loss term. And so this L1 is going to be replaced with a pump equation. So at that point, that will become a 0. The pump function here replaces the L1, and we can construct this to actually have the same behavior as L1. It's just using a different equation. And I'm calling it H over Q here. And now we would code the new model into a solution tool and proceed. So what we'll do at the next meeting is we'll go ahead and examine these changes already made in an R script, run a few examples, and then we will move into the EPANet model. In a different world, I would have liked to had you actually script these yourself, mostly so you can understand what's involved in these EPA models, and then you would never want to do it again. But because of the online semester, we have to economize with time, which I'm obviously not doing right now. I've elected to set that aside. And so I'll show it to you and explain it so that you know that these computer programs that you're using professionally, they're really not that special. I mean, there's a lot of work in them, don't get me wrong. But the work is in the interface that assembles all these equations for you. So when you're drawing a line in a network simulation model that's a pipe, what I want you to get out of it is you're really writing an equation graphically, and the computer is translating the graphical writing to the code. That's all I have for today. Let me check the chat and see if there's any questions. Either I've scared the heck out of all of you or put you to sleep. Scaring's not a good thing. If I put you to sleep, that's helpful. It's evening time anyway. And if there's no questions, I'm going to go ahead and stop my screen sharing and end the Zoom meeting. So I want to thank you very much for your patience and attention. And actually, that was a pretty good staying power. It looks like everyone that signed in at the beginning stayed with me. And the video will be posted as soon as I can get it uploaded. And have a great weekend. Have a great day tomorrow. A good weekend. And the usual, stay safe. Don't get infected. Don't infect other people. Be careful. Eventually, this will all end and we'll go back to something that resembles what we're used to in life. So take care of yourselves. Have a good weekend. I think the weather's supposed to be pretty nice this weekend, so I hope you can take advantage of that as socially distancedly safe as possible. All right, that's plenty of time for questions, so have a good evening. Goodbye.